Hey guys, welcome back. This will be the last installment that we have for this chapter before we start the next chapter, which will be next week. So you'll do this lesson at home. Just make sure that you have it done before we come back back to class, whether you're meeting on Monday and Tuesday or on Thursday and Friday. So we will be finishing this up and talking about disjoint and independent events. In this case, some of our examples are referring to blood types, so I just thought I'd give you this information. So if you know your blood type, if you've ever given blood, for instance, my blood type is A positive, just like my grades, just kidding. It's actually one of the most common blood types, the second most common, I believe. And it'll tell you what type of blood I could receive because of the antigens and the blood types, which is kind of cool. I almost showed you a picture of like somebody giving blood, but like blood makes me nauseous. All right, so anyway, we have three different types of probabilities. Personal probability is like an informal, so it's your personal degree of certainty of whether or not you think you'll get a B this semester or something like that. Do you think that's very likely or unlikely? How would you quantify that, etc. Empirical probability has to do with the random phenomenons that are observed over and over again. We can actually graph out that relative frequency, and as we increase the trial size to infinity, it will eventually settle down or converge to the true relative frequency, which we also call the empirical probability. Then we have theoretical probability, which we'll be spending most of our time dealing with, which is based on models such as dice and cards, where we know all the possible outcomes, and if it's truly randomized, like if we shuffle it, or of course the dice are reset every time, then we know that what the possible outcomes are, the number of potential or favorable outcomes over the total number of outcomes, and that'll help us with our probability. So let's do an example of that. Let's do it with Go Fish. So let's say we play the game of Go Fish, and our 5 cards are dealt. Our hand is dealt first, and then our partner draws 5 cards. So the first 5 cards out of 52 of the deck were dealt to us. So now there's only 47 cards remaining in the deck. We have an ace, and so we ask our partner them if they have an ace. And so we want to find the probability they have at least one ace, because technically they could have 2 aces or they could have 3 aces. I suppose if they had 2 aces, then they would probably put those pairs down or whatever, but we're going to continue and just guess maybe they have multiple aces. So the best way to do this is not to say the probability they have 1 ace and then find the probability they have 2 or probability 3, because then you have all the combinations. The best way to do it when you see at least one or at least once, is to find the complement. So find the probability that they don't have an ace at all. Then we're going to subtract that from 1. So the probability that they don't, so 1 minus the probability they don't have an ace. Well, the first card, there's already been 5 cards dealt. So the first card they are dealt is the 47th card. And out of 47, there are 3 aces left over, right? So how many of those are not going to be an ace because we're finding the complement? Well, that would be 44 out of 47. Then the second card that was dealt, there's only 46 cards remaining, and only 43 of those are not aces. And as you can see, the pattern just keeps decreasing, both of them by 1 each time. So when we put this in the calculator, there's 2 ways you can do it. This might be the best way. So I'm going to put it in as a fraction first. So we have in the numerator 44 times 43 times 42 times 41, and there were 5 of them all together, so we'll go to 40. And then the denominator, we have 47 times 46 times 45 times 44, and then times 43. Now it's going to give us an export as a fraction, which isn't really super helpful. So what we want to do is we want to convert that to a decimal. So if we go to math, and then decimal, convert to decimal, it'll give us a decimal. So that's going to be 0.07, whatever. I basically rounded in this case. Now that's a probability they don't have an ace. So the probability that they do have at least 1 ace is going to be 1 minus that, which is going to give us 0.292. And that's a probability they had either 1 ace, 2 aces, or all 3 of the aces, remaining aces in the deck. All right, so let's say that you ask your partner if he has an ace, and then he says no. So instead it was the almost 71% of the time, then they draw an ace. That next card they draw, what's the probability that one's going to be an ace? And then of course he'll get an ace from you the next round because he knows that you have an ace. Well, there were 43 cards left in the deck. Now there's only 42, and there are still 3 remaining aces if he said no, unless he was lying, which they're not much fun to play with if they lie, right? Only 2-year-olds lie. So 3 divided by 42, that'll give us our fraction of 7%. So we have a 29% chance that whatever card we ask, that they will have that, unless they already had a pair of them, then there's only 1 remaining, etc., etc. Then if they at the next card they draw, there's a 7% chance they will draw that card that you just asked about, and then they would end up kind of winning that round. All right, our first probability rule is that whether we're going from impossible, where the probability is 0, or certain, which probability is 1, the probability of event A occurring has to strictly be somewhere between those two. It can't be negative, can't be greater than 1. Also, the sample space, which is all the possible outcomes, the probability assignments for those have to add up to 1 for it to be a legitimate probability assignment. The complement rule says that the probability, like in this case, of having a diamond, drawing a diamond, is 1/4 of all the cards, or 25%. Then the probability of not having a diamond is 1 minus that probability, which would be 75%. So just 1 minus that one there. All right, mutually exclusive means that there's no overlap or they are disjoint, so it's impossible. So if I know that you have if your card is a heart, then I know it's impossible for it to be a diamond because we don't have any diamond heart cards. So these two are disjoint. We also say they're mutually exclusive, means they don't overlap at all. And they're not disjoint if they do overlap. That means the intersection is non-empty in that case. Then we have intersection and unions of sets. So the intersection is like and. So if I want to know what's the probability that event A and B occurs, if they're two separate events and the probability both of them occurring, if it's possible for both of them to occur, then they would have an overlap. That would be what we call the intersection. And it's this upside down U. It's just like that. Okay, so the other one we have is a regular U, which the symbol in logic means that, well, logic and in stats, I suppose, means that it is the union of the two sets. So the union of the two sets would be that it's A or B or both. If it's an inclusive OR, we're pretty much always going to deal with inclusive ORs in this case. All right, so that brings up the next funny thing. So I thought about this a lot, and I decided to make a graph, and maybe that's why I'm single, but I don't know. See what I say. So why am I single? Am I an and kind of guy or an or kind of guy? Well, there's a lot of guys out there who are not as picky as I am they're really or kind of guys. So for instance, they're looking for a gal who's smart or attractive, and so, you know, they have a much more, you know, potential mates out there. But for me, I'm an and kind of guy. They've got to be smart and attractive and a bunch of, you know, 25 other different things. And so I just keep narrowing down, and it's not, they don't exist. There's a lot of fish out there in the sea, but, you know, that's why I'm probably still single. Or is it because I make that chart? All right, so that was it. Just a quick review. Difference between mutually exclusive and independent. We'll get to that on the last part here. All right, so choose an American farm at random and measure its size. Here are the probabilities that the farm chosen falls in several acreage categories. So basically, they give us the probability assignment rule, or the probability assignments here for the acreage and their probabilities. Let A be the event that the farm is less than 50 acres, so that's going to be these two, and B be the event that it's 500 or more, which is going to be those three different categories. Find the probability of event A. Well, because these two events are mutually exclusive, because they're disjoint, there's no overlap, you can't be less than 10 and more than 10, we can just simply add those two together, which would give us 29%. Find the probability of event B. Again, these are also mutually exclusive. They're disjoint. You can't be both more than 2,000 and between 1,000 and 999. So we can just simply add them together, which will give us 18%. What condition allows us to add the probabilities in part A and part B? Well, we can add part A and part B together because those two as well are mutually exclusive, right? If you're in part A, event A, you can't be in event B because there's no overlap between those two. What condition? So that would be the events are mutually exclusive or disjoint. Those mean the same thing. Describe a complement in words. So a complement is a probability that A does not occur, which is that it is larger than 50 acres. So that the farm is more than 50 acres. Find the probability of a complement. Well, if the probability of A is 29%, then the probability that it's a complement is 1 minus that, which would give us 71%. All right, describe A or B. So this is going to be the intersection of the two, the union of the two. So what's the probability that we have a farm that is less than 50 acres or more than 500 acres? So that would be how we would describe it in words with or, because we're dealing with the union of the two, not the intersection, which would be the and, right? Find the probability of A or B by the addition rule. Well, again, we can add these together because they're disjoint, so we don't have to deal with anything with like any overlap. So 0.29 plus 0.18 is going to give us 47% altogether. On example 2, event A is the person has a cholesterol level that's a high cholesterol of 240 milligrams per DL, whatever that stands for, dialiter, I have no idea, or above. Event B is that they have borderline high cholesterol, which is anywhere from 200 to 339. And the first thing we want to do is actually fill in the diagram for this. Now, both of these are going to be mutually exclusive because you can't have borderline and also high cholesterol at the same time. You're either strictly between 200 and 239, or you're 240 and above, or you're less than that, right? Less than 200, which would be a normal cholesterol level, I believe. All right, so probability of event A, they said was 16%. So 16% of Americans, they're saying, have high cholesterol. Surprised it's not higher. And then 29% have borderline. Okay, that's kind of that makes more sense. So what percent have neither? Well, we would add these together and subtract it from 1 because you either have high cholesterol, borderline high, or neither, which would be the normal, I believe. I don't think there's a third category beyond that. All right, so explain why they're mutually exclusive. Well, they're mutually exclusive because you can't be both. You're either one or the other. There's no other overlap, in other words. A way that we can actually write that out is the probability of the intersection of those two, which is that year A and year B, is equal to 0. Okay, so statistically we can write it out like that. So they're mutually exclusive if the probability that year A and B, which is high cholesterol and borderline high cholesterol, is 0. That's not possible. They don't overlap. Explain in plain language, or say in plain language, what that means. So the union of those two means that you're A or B. So in other words, that you have high or borderline high cholesterol. Find the probability of that. Well, again, since they're mutually exclusive, we can just add them together. So 16% plus 29% will give us 45% altogether. So 45% of Americans have high or borderline high cholesterol. That's pretty sad. All right, if C is the event that the person chosen has normal cholesterol, which is below 200, then find the probability of C. So if 45% have high or borderline high, then the complement of that, 1 minus the sum of those two, will give us 55%, which is what we had left over. So 55% of Americans have a normal cholesterol level. All right, example 3. You have two sets. Set number 1 has these 5 letters, and set 2 has these 6 letters. Use the complement rule to find the probability you pick at least one vowel if you pick one letter from each set. Now, there's different combinations we could get. We could get A, or we could get E from the first one, or we could get O from the second one, or a combination of both, or because they just ask for at least one vowel. So anytime you see at least one, we should always use the complement. It's going to be much simpler. So what we're going to do is we're going to find the probability that we pick one from each and we don't get a vowel, and then we're going to subtract it from 1. So from the first set, there are 5, and out of those 5, there are 3 of them that are not vowels. And then from the second set, there are 6 altogether, and there are 5 of those that are not vowels. So if we multiply the probability that from the first one there's no vowels and no vowels from the second one, then we subtract that from 1. That'll give us a probability that we have at least one vowel if we I think I was saying valve, vowel if we pick one from each set. All right, so what we can actually do on this one's kind of nice. We can reduce these fractions before we multiply, which is going to be 1/2. All right, so that's 0.5. 1 minus 0.5 is still going to be 0.5. So there's a 50% chance we'll get at least one vowel if we pick one from each set. All right, 36, the last one I'm going to do with you guys here. Oh, we're doing really well on time too. All right, the American Red Cross says that 45% of the U.S. population has type O blood. So I'm going to go ahead and fill that in. 40% has type A, 11% type B, and then the rest is AB. Well, if the rest is AB, then there's really nothing that's not one of those types of blood, unless you have alien blood. I don't know. Where's my aluminum foil hat? So we want to add these together, subtract it from 1, and that will give us what's left over. So that's 85 and then 96. So there's 4% that have type AB blood. All right, so what's the probability someone has type AB blood? Well, we just did that, right? 4% has type A or B. A or B would be just adding them together. And again, we can just straight add them because they're mutually exclusive. You can't have type A and type B blood. All right, So that would be 51%. Is not type O. Well, type O is 45%, so not type O would be the complement. 1 minus 45 is 55%. So if we added all these others together, of course, we get 55%. All right, among 4 potential donors, what's the probability that all are type O? Well, there's a probability 45% that the first one's type O, and then 45% chance the second one would be type O. Because whenever we are sampling without replacement in this case, but because we're sampling less than 10% of the population, don't worry about that. We'll get that in a little bit. But anyway, they're independent. So whatever blood type we find for the first donor, it's not going to change the probability the next donor is going to be 45% type O as well. So these are independent events because the probability is not changing. All right. So 45% times 45% times 45 times 45 is going to give us a total of only 4.1%. So there's only a 4.1% chance that all 4 of our donors will be type O blood, even though that is the most common blood type. Because more than likely we're going to have some other blood types introduced there as well. No one has type A blood. So no one is going to be the complement of AB, which is going to be 0.96, and no one of those 4, right? So it's going to be 0.96 to the 4th power. Instead of multiplying it 0.96 times 0.96 times 0.96, you can put it in that way. It's a lot easier. So I'm going to do 0.96, and then we're going to use the caret button. Oops, what happened? Caret button, and then the 4th power, and that'll work. Alrighty, so that's the probability that no one has type AB blood. That's going to be pretty common because type A blood is really rare. So it's probably going to take more than 4 donors before we find somebody who has a type AB blood. All right, they're not all type A. So if they're not all type A, the only way that cannot happen is if they are all type A. So if type A would be, so basically we're finding at least one of them is not type A is really how that question could have been worded. And if we're doing at least one, the easiest way to do it is to find the complement. So we're going to find the probability that they are all type A and then subtract that from 1. So type A was 0.4, 0.4 to the 4th power would give us the probability that they're all type A blood, and then we subtract that from 1, which will give us that value when we put it in the calculator. And I can go ahead and show that to you if you want. So 0.4 to the 4th power, so that would be caret 4. Okay, cool. And then we're going to subtract that from 1. So 1 minus the previous answer, which is how I got the answer. All right, at least one person is type B. So again, anytime you see at least one, we're doing the complement. So find the probability that none of them are type B. So if type B is 11%, then 79% would not be. So if all 4 of them were not type B, that would be 0.79 to the 4th power, just like we did pretty much before. So 0.79 to the 4th power. So that's going to be caret 4. All right, and then we're going to do 1 minus that previous answer, and that's going to give us our answer 61 point something. All right, 0.05. All right, last one, so almost there. 38, disjoint or independent. And the last problem, you calculate the probabilities involving various blood types. Some of your answers depend on the assumption that the outcomes were disjoint. That is, that they could not both happen at the same time, or in other words, their intersection was empty. The probability of the intersection of both of them happening, event A and event B, would be 0, because you can't have type A and type B blood. Other answers depend on the assumption that the events were independent. That is, that the occurrence of one of them does not affect the probability of the other one. Do you understand the difference between disjoint and independent? So if you examine one person, are the events that person is type A and that the person is also at the same time type B, disjoint, independent, or neither? Well, in this case, because it's not possible to be both of them, that would be that they are disjoint. So if you look down here, all of these are disjoint. They're not overlapping because you can't be type A and type B for the same person. But if we're talking about 2 different people, so if you examine 2 people and the events that the first one's type A and the second one is type B, that is possible because you're talking about 2 different people. So the probability the first one is type A is 40%. Probability the second one is type B is 11%. So if they're independent, meaning if the first person is type A, it's not going to change the probability of the next person being type B. We do see those probabilities changing. Let me go ahead and do that real quick. I'll show you. We do see those probabilities changing. Let me go to our example with Go Fish. Yeah, see, the probabilities change once we draw cards, right? Because there's no longer the same amount of cards left in the deck, nor would there be the same number of non-aces that are in the deck. So after each draw, it's not independent, because your likelihood of running into an ace is actually going to increase the more cards that you remove that are non-aces. Okay, so this would be an example of when we're drawing without replacement and when it's not going to be independent events. However, when we're dealing with, like we were this one, with type A and type B blood with two different people, in this case, regardless of whatever blood type the first person was, that's not going to change the probability for the blood type for the second one. So then we can use our multiplication rule, because we're assuming they're independent events, and they are. And so 40% of 11% would be 0.044, and we could put that in the calculator if we wanted to. So 0.11 times 0.4, so 40% of 11% is 0.044. So there's a 0.044 probability that we have. If we sample two people, one of them will be type A and the other one will be type B. Can disjoint events ever be independent? Well, the problem is that disjoint events they're mutually exclusive. They don't overlap. But in order for events to be independent, it has to be possible for both of them to occur. And in fact, if they're mutually exclusive, the probability of both of them occurring is 0. So think about it that way. If you tell me that you have type A blood, what's the probability you have type B blood? Well, it actually goes to 0, because you told me you already had type A blood. So it's not possible for you to have type B blood. So whether or not I know your blood type does change the probability of your blood types. It completely changes it. So mutually exclusive is when they don't overlap. That's when we're wanting to add them together with the general rules we have right now. And then multiplication rule requires an independence assumption, which is that knowing that one event occurs does not change the likelihood of the other one occurring as well. All right, so that's all that I have for you today. Decent, a little bit shorter on this. We'll start the next chapter together in class. We'll do the 2 lessons together for the A students. It was really nice seeing you guys in class today, the A students and the B students that I saw. So thank you. Makes it a whole lot easier on me, keeps me motivated. But if you're staying at home, just let me know if you have any questions, because you're still my student. And so I want to make sure that you're successful this year. So I'll see you guys later. Have a good day.